Welcome to lecture 4.8. In this video, I'll be covering why electron donor groups are typically Ortho-Para directors. Just like the last video, there are two general ways to approach this question. First, we'll start by looking at the starting material reactivity. Now here, we have a strong activating group due to the fact that there is a lone pair directly conjugated to the benzene ring system. Let's look at the different resonance forms that this lone pair being there can actually lead to. First, we can take one of those lone pairs, make a double bond with the oxygen, and then push one of the benzene pi bonds to the ortho position. Drawing this out, we can see that the oxygen will take on a positive charge, and the carbon on the ortho position will gain a negative charge. We're not done yet, though. Now, remember, last time we were able to move this bond over. That isn't going to work this time, right? This is a full, highly electron-dense carbon with a lone pair. We can move it to make a pi bond, and then break this pi bond to give the atom at the bottom, or the one that is para to the OH. It can gain the electrons instead. Right. Resonance is clearly an important topic in this course. Keeps showing up. And last but not least, we can move that lone pair one more time to get a negative partial charge on that ortho position. So, looking at these resonance forms, once again we see this pattern where we have a stable neutral resonance form that's clearly going to dominate, but three different resonance forms that will put partial charges on our overall hybrid. Drawing that hybrid, here's the phenol structure. Three of these resonance forms, all three of them, put a delta positive charge on the oxygen, showing that it's less electron dense than you may expect. And more interestingly, a delta negative charge on the ortho and para positions. So just like before with the meta-directors, only the ortho and para positions are being given this partial charge by resonance. Well, then what's the difference? The difference is these were delta positive charges. We were deactivating the ortho and para positions when we used an electron withdrawing group. Notice now that since benzene is a nucleophile, nucleophiles are better when they have more electron density, we are now selectively activating the ortho and para positions, making them more reactive and more likely to participate in these EAS reactions. So that's how we can approach this, by looking at the starting material's reactivity. I do want to cover one quick exception to these rules that I've laid out. So far, I have said that activators, right, so I'll say this up here, activators are ortho-para directing, and deactivators are meta-directing. And this is virtually universally true except for the halogens. The halogens, briefly, are weakly deactivating. They are weak deactivators, kind of like how the R group or the alkyl group is a weak activator. They reduce the reactivity of the benzene ring slightly. However, they are still ortho-para directing. We can handle this by looking at the intermediate of the reaction. So here, based on this intermediate, we can imagine this pi bond may have attacked some electrophile. So we have to imagine that electrophile being present. However, that positive charge being there is something that the bromine is actually capable of stabilizing, right? The bromine can use its lone pair, kind of like how oxygen would, right, to make a resonance form. Now the difference is that if this was an oxygen, right, so let's take a pause here and imagine that this was an oxygen instead, right? This resonance form would actually be very strong. Oxygen loves to participate in resonance when it stabilizes charges. However, bromine isn't, the other halogens, bromine and chlorine, they are very poor at resonance. So this is a very minor form compared to if it was oxygen. Basically, what this leads to is the idea that this is still a deactivating ring or a deactivating substituent, but nonetheless an ortho-para director. Be aware of that one quick little exception. We'll cover that again when looking at all the groups together in video 4.9, or the number line of activation. That kind of teased a similar idea, but let's talk about the stability of carbocation intermediates instead. right? Very similar idea here. Now we're looking at the NH2 group, and we're investigating which pathway would be better, not by looking at the reactant, as we did above, but by instead looking at the stability of its intermediates. Looking at this position, we can quickly see, and I'll avoid drawing the full resonance forms here. We can move the positive charge to this position with that resonance form. And once we have that, this could then move to put positive character there. Notice how these are ortho and para positions that are positive. When drawing the overall hybrid, right? Or actually, I'll avoid the overall hybrid here. What I will say is that at no point are these positive charges really dealt with. Do they ever interact with the nitrogen, right? Let's look at this case, though, when we put that group para, which we know is preferred. When I draw this resonance form, and this is the key one to pay attention to, I generate a unique resonance form we didn't see above, which is that the positive charge is beside the NH2 group. Now, coming at this with the electron withdrawing perspective, this may seem bad. After all, nitrogen is more electronegative than carbon and can pull electrons away. That was destabilizing. However, this is not an electron withdrawing group. It has a lone pair, and it will absolutely donate it in resonance. And this is why it's such a strong group, such a strong activator. Right? Stronger than the R group, because this resonance form is incredibly stable compared to all the other ones. Recall that positive charges are very unstable due to the fact that they are octet violations. This resonance form is by and large the more dominant one because nitrogen doesn't like necessarily being positive, but it's not an octet violation. It is much more stable, and therefore, by adding these electrophiles to the para position, you get a much more stable carbocation intermediate. The same is true for the ortho position if you draw those resonance forms out. Now, real quick, before we go any further, I want to mention the idea and compare between the ortho and para positions for the ortho-para directors. Generally, either is correct. If you put one in a position that's suboptimal, we'll talk about what that means, it shouldn't be a huge deal. Usually you'll get the marks for that on any test. But there is another consideration to consider, and that is sterics, or the location of things in space. Let's look at this example where we're taking this benzene that's been alkylated with an isopropyl group, and we're doing a sulfation reaction. Generally, para is better, and the reason for that is simply that these two groups are far away from each other. They're not going to interact with each other and prevent chemistry from occurring. The ortho position still occurs in decent yield, and of course that depends on the groups and the conditions. These are just ballpark numbers. I wouldn't put much stake in them. But of course, the meta position would be incorrect. If you tried to make the meta substituted product, well, you wouldn't get very good yield at all. It would be mostly waste. So that's great. For mono-substituted benzene, para is always better than ortho. But keep in mind that once we have more than two groups, this becomes much less of a hard rule. It's not that para is always better than ortho. It's just that you want to put the group in a position that agrees with the ortho-para selectivity and is as far away from the other groups as possible. Just be aware that this para being better than ortho rule you may have heard about in lecture is only true for when you're dealing with a mono-substituted benzene. If your options are close and far, far is always the better option. With that in mind, let's put all this idea together, everything from video 4.6 to now, into the next video, and I'll show you the number line of activation and how to handle multiple directors at the same time. It's easier than you might think, so I'll see you there.